Am I audible? Hello. Am I audible?
Yes, sir. Audible, sir.
Yes, sir. Audible.
So, we were looking at the first session. So, here we saw that here we saw that this is the loss. So we have a loss function, and now what is our objective? Our objective is to minimize the loss function. So we want to minimize the loss function. Now, what will happen if so? This is like this. This equation is. And what will happen if the output is 1? So if the expected output is 1, so we want to minimize this loss function. So our actual output should be in such a manner that this function is minimized. Okay. So now what will be our actual output? So here 1 minus 1, this becomes 0, right? So here we will be left with minus log y dash, right? So this will be our actual, this will be the value that can be computed in the loss function. This should be minimum. In order to make this minimum, what should be our y dash? Y dash should be maximum. What is the maximum value that y dash can take? How do you compute y dash? Y dash is equal to sigma of z. So this is what we saw earlier. So y dash is going to be equal to sigma of z. So we have in this particular case uh, uh, we have delay. So you have w and x. So you have wx plus b, which is equal to z. Then sigma of z. So now sigma of z is equal to a, which is the activation. So now this is also equal to y dash. So now y dash should be maximum in order to make the loss function minimum. If y equal to 1, y dash should be maximum in order to make the loss function minimum. So if y is maximum, the loss function minimum. Now if y is equal to 0, then what will happen to the loss function? This becomes 0. Now this becomes minus log 1 minus y dash. Now what should be the value of y dash? Y dash should be, so if y dash is maximum, then what will happen? If y dash is maximum, then this value will not be that much minimum. But when y dash is minimum, say for instance, y dash is 0, hello? When y dash is 0, then this entire becomes more minimum. Right? In order to make this entire thing minimum, y dash should be minimum, by which way 1 minus y dash will be larger. So y dash should be smaller. So only then it will make this loss function minimum. Right? So if y dash y is equal to 0 also, you are able to make the loss function minimum by having y dash to be smaller. If y equal to 1, once more you are able to make the loss function minimum by having y dash maximum, right? So since this is able to satisfy both the things, like you have this as the loss function. This is one thing I wanted to clarify. Then another thing is with respect to this. So over here, so what do we have here? So what is the loss function? We have y log y dash plus 1 minus y log 1 minus y dash. Thing. Okay. Now, what is this a? A is equal to y dash, right? As I already told you, we have z. Z is wx plus b. Then we have a equal to sigma of z, right? Then we are computing the loss function. Right? So now here you have the loss function. Now, so loss function is normally we see loss function as L of y dash comma y. So where y dash is the computed output and y is the expected output. So now we have this as the loss function. So L of y comma y dash is computed using this function. Now in place of y dash, what do you have? We have a, right? So you substitute in place of y dash, you can substitute a. So now we compute dou L by or dl by dA. So now when you compute dl by dA, what do you get? You get this equation, minus y divided by a. Here there is a minus, and over from here you get another minus. So you have minus minus plus 1 minus y divided by 1 minus a. So you have this particular. Now, in order to find out how much L has varied with respect to a, I compute dl by dA. Now I need to compute dl by dz. How much L has varied with respect to dz. Right? So in order to compute dl by dz, what do I compute? I compute dl by dA into dA by, using the chain rule. So now, now when we compute this one, what we get is that we have dA by dz. We have already computed this one. So this is minus y divided by a plus 1 minus y divided by 1 minus a. So dA by dz, that is given by, you can try to solve this. So what is a? A is equal to 1 divided by 1 plus e power minus z. So you can find out d by dz. What is this value? This will be equal to a into 1 minus a. Right? So you can simplify and check like whether this is same. So now if you multiply this one and this function, then for dl by dz you get a minus. So another thing that we need to note is, you normally write dl by dz as dl by dA is written as dA. Similarly, dl by dw is simply written as dw. dl by dw1 is simply written as dw. So if somewhere it's written dz, so the dz over here is basically dl by d. So now, uh, now Now we've compared dl by dz, dl by dA. Now what we need to compute, how much W1 has affected dl. So dl by dw1. So dl by dw1 is computed by dl by dA, a by dz, dz by dw. So by chain rule, this is what gives you dl by dw. Right? So now this entire thing can be written as dz. So by because you know that dl by dz is equal to dl by dA into dA by dz. So this entire thing can be written as dz. So dz by w1. So if you differentiate this equation, then you get x1. So that is why you have in here dl by dw1 is equal to x1 into dz. Similarly, for w2 also, dl by dw2 is equal to x2 into. On the other hand, with respect to b, if you differentiate, you will get 1. So db dl by db, this you can also write as db. db is equal to. So we have this, and this and this equations. So this is what we write over here. So you have dA is given by this particular equation. dz is given by a minus y. dw1 is given by this equation, and this equation. So you have these derivations. So now Now, why do we compute this? We compute to basically find out the gradient, right? So why do we compute all this? I want to make modifications in W1, W2, and V. If I want to make modifications in W1, W2, and V, then I need to find out dW1, dW2, and dB. And in order to find out dW1, I need to find out dZ, and in order to find out dZ, I need to find out dA. Right? So that's why, like, that is how the back propagation is useful. Like propagating from the back is useful because that effectively leads to the computation of all these variables, all these different derivatives, right? So now, having computed all of is what we can do. So this is for an individual example. Now for M training examples, you compute all the individual derivatives and you sum all derivatives. So for each of the variables, like find out the derivative and you sum all these derivatives, and eventually after M examples are being used, you divide it by, and then you do a weight update. So this will be now coming over here. We saw, so that is with respect to the logistic. Now with respect to a neural network, so you have a forward propagation, and then you have a back propagation. So in the back propagation, you compute the derivatives. Now over here, you have two layers. In the earlier case, we had only one layer, right? So the weights in the first layer is denoted by W1. Weights in the second layer is denoted by the square bracket W2. Now, similarly, the bias in the first layer is denoted by B square bracket 1. Bias in the second layer is denoted by B square bracket 2. So now, uh, having found out all this, like we'll be able to do a forward, and then like we can do a when we do a back propagation. Before that, like we get the activation function. So now back propagation may come encounter different types of activation. Then we also looked at why we require a nonlinear activation. Then we looked at this particular aspect also, the derivative of the activation. So before we look at this derivative for the activation, one other thing like we will see. So which is the somebody asked about the cost. So now we have over here, like we have the logistic regression cost. So the logistic regression cost function was y this thing minus y log plus minus this was logistic regression. Now we have y cap, which is given by sigma of w transpose x plus, and sigma of z was given by 1 divided by 1 plus e power z. So we have the y cap that is defined by, so this was z. So now how do we interpret? Say for instance, y cap is equal to 0.6. Now what is this 0.6? It is a probability. What is this probability? Okay, so we already saw that like sigmoid is going to have values ranging from 0 up till 1, and if y cap is 0.6, then what is this probability? This probability is the probability that you have a cat given x, right? So if you have a problem that you want to determine whether a given thing is a cat or not, then we interpret it, interpret the value, the output of the model. So you have a model, right? So you give some input, you get some output. This output is y cap or y dash, right? The output of this model is said to be interpreted as probability of y being a cat given x, right? Y is equal to 1 given x. So now if you can say it another way also, if y is equal to 1, the probability that y given x is given by y bar, and if y is equal to 0, the probability that y given x is given by 1 minus y bar. So this is another way to say the same thing. This thing, you can say it this way. If y equal to 1, if the output is a cat, if the original output is a cat, then the probability that you obtain gives you the probability that it is a cat. If the original output is not a cat, then the probability that you obtain is to be subtracted from -1 in order to get the probability that it is not a cat. Okay, so I think it's clear, right? So this two statements say it this way, that if y equal to 1, if output is a cat, then the probability that it's a cat is given by y cap. If output is not a cat, then the probability that it's not a cat is given by 1 minus y cap. So y cap is the chance that y equal to 1, and 1 minus y cap is the chance that y equal to. So now if you want to put this together, right? So in a single equation, then y given x can be given by y cap over y, 1 minus y cap, 1 minus. So this equation is going to capture these two statements. These two statements are captured by this one equation. So how is that it captures these both the things? If y equal to 1, then what will happen to this particular equation? This part of the equation, so 1 minus 1 is going to be 0. So something for 0, you have a 1 here. Now y cap power y, so you're going to have uh, y cap. Right? So if y equal to 1, then your y cap is going to be the. On the other hand, if y equal to 0, then you're going to have over here, this will become a 1. Right? So y power 0 is going to be 1. Then over here, you're going to have 1 minus 0. So you're going to have 1 minus. So it means these two statements have been captured by this single equation. So now this single equation, it can be written in log form. So you can write it in log form as log p of y given x is equal to, you can write it as y log um, as 1 minus y log minus. So you can write this in this. Now you put a minus before this, basically because, so now by doing this, like the meaning of this equation is not changed. Having a minus before this, like you make this function a function that needs to be minimized. So in order to make this a function that needs to be minimized, the minus before this, and so you have a loss function that is given by I comma. So that's how like we use this as the loss function for this particular logistic equation. Now we arrive at our where we left. So we left it at this particular place. So we saw that neural network like different activation functions. You can have different activation functions. You can have derivatives. Right? Say one another thing I can say. This is with respect to the non-linearity. So say for instance, like why do we need a non-linear activation? Say for instance, if we have A1, so what is this? This is the first layer activation. So first layer activation is basically sigma of Z1. If the first layer activation was a linear function, then here we are going to have Z1 itself, because Z1 is a linear function. So what is Z1? Z1 is going to be lambda x plus e. So you're going to have, if you do not have any kind of a function here, so say for instance, like here we make a generalized function g. So now if you have a linear function, then you may have this itself. So this is given by W1 x plus. So indeed, this is the first layer weights and first layer bias. Now, this is going to be the input to the next layer, right? So you have A2 is going to be equal to, once more, let's assume that you have a linear function. So assuming linear function. So you have um, uh, Z2. Z2 is going to be A1 plus. So this is going to be here. So this is going to be the input to the next layer, right? Say for instance, like you have this is going to be A1. So now you have another network. So this is going to be, let's assume here you have weight 1, here you have weight 2. Then the output here is going to be A1 into W plus. So that's what we so now, given that like you have this function, now what we can do, we can substitute this weight over here, right? So we have W2 into W1 x plus B1 plus B2. So this is going to be. Now we can write this as W2 into W1 into x plus W2 into B1 plus B. Now what you can do, this you can write as W dash x plus this entire thing you can call it as dash. So what do we have? We have once more a linear function. So now here we had a hidden layer. This hidden layer was a linear function. This used a linear function. And in the output layer also we had a linear function. Now since you had a linear function, it in the hidden layer it did not introduce any kind of a non-linearity. So the result is also a linear so how many number of hidden layers you have, if you have only linear function, the result is always going to be linear. So that is why we need to introduce some kind of a non-linearity. So if you want your neural network to learn complex patterns, you need to have non-linear. You need to introduce. Otherwise, like it will be only be able to learn straight line. So that is now here we can note few things. So you look at the derivatives. So the derivatives of the ReLU. So g dash of z is 0 if z is less than. So we have a ReLU function that is like this. So the ReLU function like this. So if g dash of z is the derivative is 0 if z is less than 0, 1 if z is greater than or equal to. Now similarly, like we can find out we can see with respect to leaky ReLU also. So if it's negative, then you have, so what is the leaky ReLU function? If it's less than 0, you have 0.01 into z. So now finding out the derivative with respect to z, you have the slope as 0.07 if z is less than theta, and 1 because you have z, and finding the derivative you have 1 if z is greater than equal to 0. So now we'll further move. So so we look at these derivations. So if you look at these derivations, you will see here. So these are the derivations. So it means that in order to compute the output from neural network, so you are going to have Z1, then you're going to have A1. We assume a neural network with a single neural layer. So then you assume Z2, then you assume A2, then you have L of Y, comma. So you find out this now, having found out the output, like you will be once more going back and doing the back propagation. So you have a forward loop. So where you find out Z1, then over here you find out A1. Here it's written as G of Z1. So to make it more general, right, you can have a ReLU function. Then you have another Z calculation. Then you have A2 calculation. So here you have a sigmoid equation. Now you compute, you do the. So since you have a, you will see that this step. So it means now you compute dou L by dou. So initially like dou L by A, and you'll be computing dou L by. So now you also will be computing dou. So A2 Z2 dou L by dou W2 dou L by dou W1. Then you may be similarly. So B2, so W2 B2. So similarly, like you'll be computing DZ1 is dou L by dou Z1 and dou L by dou in this kind of So also dou L by dou. So we see the pattern, right? So dou L by dou A1, dou L, sorry, A2, dou L by dou Z2, dou L by dou W2, P2, A1, W1, V1, and Z. So we see the pattern. So we do a back propagation and we compute in this kind of a. So if you look at like what is being computed, these three things are similar to what has been computed earlier. So A2 minus Y is what we saw. So this is same in the logistic regression case. So in the logistic regression case also, in the last two layers were very similar to like what was there in logistic. So we see that the Z2 was A1 minus Y. So here you have A2 minus Y. So dW2 was X1 into dz, right? So in the earlier case, it was X into dz. So here we compute dz2 into A1 because that was the input. So now similarly, dB2, dB in the logistic regression was dz. So here what are we doing? We are summing all the dz's. So in with respect to these three, like it was quite similar. Now looking at these cases also, we see a pattern, right? So the pattern is that we see dz1 is equal to w2 dz into g dash z1. G dash is basically this activation function. So A1 is going to be equal to G of Z. So the prime of this, I mean the derivative of this particular activation function. So similarly, like you also find this quite similar to what we have here. Right? So now the thing is that how many other layers that we are going to have, we are going to have the back propagation that is going to happen using this kind of a set of elements. So that is what is the inference from this. So if you have a logistic regression or if you have a sigmoid function in the last layer, then with respect to the last computations, you are going to have these derivatives, and with respect to rest of all the blocks, you are going to have these derivatives that are to be computed. So depending upon like what your input is, maybe you will have either activation outputs or you may have the input. So this is going to be the pattern that is with respect to neural network. So now we come to initializing. So how do we initialize this? With respect to logistic regression, um, how we initialized the weights was that weights were to be input with 0 and the bias terms also could be given as 0. But with respect to the neural network, you cannot afford to initialize the weights with, so you cannot afford to initialize the weights with 0. On the other hand, initializing the bias with 0 is, so if we initialize the weights with zeros in a neural network, then it's going to be difficult. Say for instance, like if you have a neural network, so so, having a neural network, Now, in this particular neural network, if you're initializing the weights with 0, that can create something called as a symmetry, right? So because you are initializing these weights with zeros, even if you have several layers, what it may compute is may compute the same thing. And when you do a back propagation, there could be very identical updations. So it means that all these weights are going to be updated identically, right? So there is not going to be any change, right? So it means all hidden units will be completely identical, and it may compute the same. So and on each gradient descent, both on the forward pass as well as the backward pass, is going to update the same way. So it means that all the weights are going to be identical in a layer. So what we do is like you initialize the weights with small random numbers. So maybe like you have this kind of random initialization and you make the numbers small. Now, even though like with respect to B, it's not at all an issue. Like you can have zeros as the initialization. Now, another thing is that you cannot have too large value for um, uh, now with if you have too large, sorry, with you cannot have too large value for W's, right? So if you have too large values for W's, then Z becomes large, and then you will reach this particular position, right? So either if you use the tan H function or a sigmoid activation function, you will reach this particular place, and then in the contour, you will not go towards the minimum. So it's going to be taking a long time in order to learn. So it means that it will result in slowing down of the learning. So now, if the weights become too large or even too small, for that matter, it's going to have an effect like this. So you typically like it's permitted to have a value of 0.01 for. Now we come to the next thing, like which is with respect to a L layer neural network. So with respect to a L layer neural network, the forward propagation is going to be in this manner, as we saw, like as it is similar to what we saw. Yeah? So we are going to have Z is equal to W into A plus B. So A of L minus 1. So then we are going to have G of A. It's going to be then now we can do it parallelly also, like say for YAM inputs, like parallelly using it is. So 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 in this particular case, what you do is like you input from the previous layer and you create an output, and then like um, you cache these values because they'll be coming in handy when you're doing a backward propagation. So these values may be useful, say for instance, dz, and so it will be helpful in computing these values. So what you do is like you cache these values in a large network. You do is you compute, do a forward propagation, as you do a forward propagation, you store these values in some variables. Otherwise, you may need to once more compute these. So what you do is like you keep these values in order to use them while doing forward. So the steps are going to be simple because we already know like what the steps are going to be. So in the forward propagation step, we are going to compute the W's and P's like as you go forward. The backward propagation step, like using these cached values that come from the forward propagation, you also compute the derivatives, and as you compute the dz and dAs, you also compute dw and db, and subsequently like you update these rates. So basically, like in neural network, you're going to have a forward propagation and a backward propagation, and you are going to update the compute the expressions, and the backward propagation is going to compute the derivatives, and using these derivatives you are going to update the weights at every layer, and keep on checking like, if the cost function is monotonically. So now if you look at the parameters, so the parameters of a neural network are, so the hyperparameters are the rate. So learning rate is what is this alpha, which is used the updation of the weights. So the learning rate and the number of iterations. So it can also be a hyperparameter, right? Then you can have you can decide on like what should be the number of hidden layers, number of hidden units in each of the layer, and choice of the activation function, and you can have these as the various um, hyperparameters. So with this, like the first thing I'm closing. So now we'll look at these. So now, if um, you typically look at the machine learning problems, so what you have is you have these three types of data sets. So you have a training data set, you have a development data set, and you have a test data set. You may call this as a validation data set, or you may call it a whole data set. So now, in general, like we find that once you select a model, so you cannot uh, get all hyperparameters at the first time. So first time, like when you're going through this model, you have several hyperparameters that are chosen. You will not be able to get all the hyperparameters right in the past. So you need to go through a loop. So you need to iteratively go through this loop. And what is this loop? This loop is basically called as idea. So you have an idea, code it, you experiment it, now you change. That may be an idea. Once more, you change it in the code. Once more, you experiment it, and so on. So this loop has to be iteratively followed in order for you to figure out the hyperparameters. So, I mean, and for every application, so for every application, so we can find that the hyperparameters can be, so the hyperparameters which work for one application may not work for another. So you need to really figure out like what should be. So now in this figuring out, like we need to use data, and there are three types of data that are used. You have a training data set, then you have data set testing. So now basically like what you do is we build a model upon the training data set, and you optimize the hyperparameters on the development data set, and after your model is ready, you evaluate your model on the test. So basically like you train your model on the training set. Then after training your model, so you may train your model, you may train another model, model 1 with some hyperparameters, model 2 with some hyperparameters, or model 1 says a model with some hyperparameter values, model 2 defines the same model with different hyperparameter values, another same model with third set of hyperparameter values, and so on. You train on the same data set, and then use this data set called as the validation data set in order to check and compare which among these models is the, the traditional kind of time. They were using these kind of three data sets for training, for development, for testing. So now, uh, now this way, like you try to optimize the hyperparameters. So this way, like you try to find out which should be the set of hyperparameters that should be. So now the size of the data set, on the other hand, like size of the data set is 100 to 1 million, then normally like the trend is to have this kind of a proportion of data division, right? So 60% for training, 20% for validation. Then, so if the size of the data set is more than this, then you can go for a division like this. Now, it is that we may choose this kind of a division, like with increase in the total amount of data that is. But the important thing is this. So you can find that many of the results that may be published, right? So they may have the testing and the development data set may come from, say, or sorry, they may have the, they can have, if you have the data that comes from a different distribution, then you are going to have very poor, say, for instance, like you have the training data set, and it comes from a different distribution, and your development data set, it comes from a different distribution, then you are going to have very poor results. More importantly, if development data set and the test data set, if both of them come from a different distribution, then it's going to be a catastrophic failure. So the effects are going to be very catastrophic, because you have the development set that comes from a different distribution and test set that comes from a different distribution. So eventually, like it may not work well. Say if the development data set comes from the same distribution as the training data set, then your model may not work well for the test data set. So it is important to ensure that the development, the test data set come from the same distribution. So even if the training and development doesn't come from the same distribution, you will be able to figure it out. Right? Because with respect to training, you may have good results, and with respect to development, you may have poor results. Right? So that way, you'll be able to figure out that the training and the development data set are from two different distributions. On the other hand, if development and test come from different distributions, it will be difficult. So it is important that you have your development and test data set. So now you can also have only a development set without a test set at all. So I mean, most of the people do this way these days. So without having development, without having only using a development result as test data set result. Now we have this concept of bias and variance. So now here we have a definition of bias and variance with respect to the underfitting and overfitting. So if your model is underfitting, so it means that your model has a high bias. So on the other hand, if your model is overfitting, then it has a very high bias. So now, if your model is all right, if you can balance between the bias, traditionally, this was the thought. So traditionally, it was thought that you need to balance the bias and the variance because you cannot have the best of both. So it's always better to have low bias and low variance while also uh, being able to cater to the concept of generalizability. So that your model should be generalizable and your model should have bias. If your model has very high bias, then it means that the model uh, may not have learned. It may not be capable of learning is also another influence that if you can derive if your model is underfitting even after training it with learning. So we can say that like the model has a high bias. Now, on the other hand, model is fitting, then we can say that your model has a high variance. Say, for instance, like you have this example. So here you have a line that separates these two classes, and you can find, you can say that like line is too simple a model. I mean, this too simple model to separate these two classes because this led to several errors. So on the other hand, you have another model. See that with some minimal errors, so you are able to separate or you are able to have a decision boundary which separates these two classes. On the third hand, like you have another decision boundary which very clearly separates these two classes. So, but we can see that like it suffers from high variance. Say, for instance, if you have another set of data from the same distribution with another so here, then next time it will learn it in this kind of. So it means that it has high variance and it overfits the data and high bias. So normally, like say we say that traditionally we say that you cannot have a low bias, low variance system, because if you have a low variance system, then low bias system, then you are going to have a high variance system. You're going to have a low variance system, then you're going to have a high system. So traditionally, like they say that these two. So what they used to do is they always used to balance the bias in the bias. So here, here another way to look at it is in terms of, say, for instance, here in this case, you're able to do a 2D plot and you're able to look at the bias in the variance. On the other hand, if you are not able to do a 2D plot, then what you have, you can have some information with respect to the training error and the development error, and then you can have some inference with respect to the high variance and so here your model performs very well with respect to the training, but it performs very poorly with respect to the development. So it means that the model is suffering from both. So here we find that the model is performing equally well with respect to data. It has sort of similar errors. But the thing is, if here you're having the bias error at say 1%. For instance, if a human being can have very less error, then we say that system is having a high bias. So it means that it has not learned as good as the. So it means with reference. So just by not looking at the training error and the dev error, but by comparing their errors with respect to a human being, like we will be able to say whether a model has a high bias. Now another case is that like here you have another model which has a high bias. Right? So training error is 15% and also has a very high. So it means that like errors of this case, then can once more say that like. So now what is acceptable is that like you have a very low training error and development error, then this is, and say if you have a bias error, say 1%, then this is an acceptable. So it means that you always use the human error as the basic. Now, these are some of the tips in order to solve the problem. So if your algorithm has a high bias, then it means that your model is under fitting. So it means that your model is not capable of learning. It may mean this, right? So now in this particular case, what you're going to do is you're going to make your network bigger. So we have seen this, right? So smaller models always underfit. So complex models always may overfit. So we can say that if you want to come out of underfitting, then one solution is to make your increase the size of the hidden units, increase the number of layers. And so otherwise, like if you're not able, if that is not possible, then you can choose another. You can choose another model that is suitable for So this is another way to overcome this. This may help or may not help is to try it longer. So the more you run, I mean, if you have a monotonically decreasing uh, cost function, then like you may arrive at something, but after a long time. So one possible way is to try time, even though like it does not always work very well. Or you can go for other organization. Basically, like you need to find out the optimal rates. So maybe your system is suffering due to improper optimization. Maybe it's not able to put the right optimal weights due to some other issue. So in that case, like what you can do is you can go for advanced optimization. So so we if your algorithm has a high variance, then there are certain possibilities that are there. One is that like you can try more data, you can try to make your system learn well, right? So learn more. There is one possibility, right? So your algorithm is already suffering from high variance, may be due to less data. So this could be a possibility. Say if you have a model and you have very less data, then if you have a fairly complex model and if you have less data, then this fairly complex model can easily learn the data. So it may easily learn the pattern that is there in the data, and this may result in a high variance. This may result in overfitting, and due to overfitting, like you have high variance. So one possibility is to increase the size of the data set so that your uh, model is able to reduce its. So another possibility is to try regularization. So it means that to reduce the overfitting, so you make the weights to not become compromise bias. Okay, like it's not so. There are techniques for solving the bias and the variance problem, so as to make it useful for learning. So uh, so it is possible to bring the bias and the variance. So The first technique in order to reduce the variance, we call this regularization. So, with respect to regularization, like we have this thing called as L1 regularization, and so it's by adding a L2 norm or a so with respect, if you use a L2 norm, and you also call it L2 norm, you also call it a Frobenius. So in order to do regularization, so what you do is you make changes with respect to the cost function. So so far, like we saw was that cost function was computed by 1 divided by m into sigma of all the loss values for all the training examples. So m training examples are there. You compute the loss function, you divide it by then you get the so by minimizing this, like that was our objective. Now you not only have to minimize only this, but you also add expression. So you have lambda divided by m into sigma is equal to x by so this is called as the regularization parameter, and this we know as the total number of this we know. So this with respect to like so this is with respect to the logistic. So with respect to logistic regression, we know that it's good. So uh, and this is the number of inputs. So you have this as the regularization. So now, based on so what is the impact of having this regularization? So having this regularization function also means that your weight update is going to so your weight update is so this we will see. For that, we see that regularization makes a lot of W values to become, which makes the model size. So regularization has the effect that it makes the W values. So how do I make my model not to overfit by making my W suboptimal? So in order to make my W value suboptimal, like I can zero, which is similar to having a smaller model. So I have a right. So this model has over. Now it means that I need to reduce the size of the model. So in order to reduce the size of the model, I make the activation function, or I try to make the weights equal to 0. If I make the weights equal to 0, then many of the weights in this model are going to be 0, and that way, like I'm going to have a suboptimal, which cannot, which will not. So that is my object. So by having W value which is 0, I make the size. So now we also see that the L2 regularization is being in general, like we see that used, and we also see that lambda is called as the regularization parameter. So it's called as a regularization. So now, if you look at the regularization for a neural network, so if you look at the regularization for a neural network, then we see a similar kind of a function with respect to cost function. And then we also have change in the derivatives. So earlier, like we did not have this in the derivative. So we only had, say, dw into, so sometimes like with respect to dw, we basically had only this. So now we also have another term. So how did we arrive at this term? This term was arrived at by 12 by W. L now has a lambda term. So it is regularization. So it means that when you differentiate the loss function with respect to the weight, now it means that like we have some additional terms in addition to whatever that came from. We have terms that are once we find out these derivatives, so so it means learning weight update consists of WL minus learning weight, and then we also have lambda m into W. So uh, so now one thing is that, so you see that what it does is, so see that WL is equal minus learning rate alpha into. So now we write this as equal to WL minus alpha, uh, um, say you have a thing which is lambda by m into W. Right? So basically what you're doing is this lambda is further taking away something from the weight. So you have a negative term. Earlier you had something only. Now you also have a lambda, which is also lambda term, which is the regularization, which is due to the regularization parameter. Now this is further subtracting something from the already existing WL. So it means that this penalizes large weights and it effectively limits the freedom. So it means it causes the weight to decay in proportion to the size of the weight. So if the weight is more, then it will decay more. Weight is less, then it may decay. So now, now this is quite straightforward in the sense that our objective itself is to reduce the weights. So make the weights suboptimal. So that you can introduce some amount of generalizability. So next thing that we see is the intuition behind regularization. If the lambda is too large, a large number of W's which will make them as just discussed. So now it means that it will behave as close to logistic. So now if lambda is good enough, it will just reduce some weights which make the neural network able to arrive at the right then without affecting the mood. So the other intuition is that we have a manage function. So if you have you want the values which are in this particular. So if lambda is too large, W will be too. So if W is too low, Z will be too low, and so then you may have the activation values that may be within this. So so basically, like if lambda is too large, then W is small, and they will use the linear part of the tanh activation. So now it will go from the nonlinear activation to linear. So it means that you are once more making your neural network suboptimal. So we see that regularization by virtue of analyzing the weights, it is trying to reduce the complexity. So this way it tries to reduce the regularization by penalizing the weights, it uses the work and it penalizes. So now there is another concept like which is called as dropout regularization. So now in dropout regularization, what is being done is that eliminate some of the neurons or the based on probability, like dropout regularization eliminates some of the neurons. So now, so one is to say you have is and you have connections. So this interconnection. So one way to make the network suboptimal is to reduce all these like this. Say for instance, now this particular neuron has been dropped out, right? So it means all the interconnections that were there have also been, all the weights that could have been learned, all have been dropped. So this way, like in every layer, we can remove some of the, so this you call as, this has the same effect as what you do with respect to regularization. You make the weights equal to 0 or weights close to 0. Like what you do is you make, you remove certain neurons. So one of the common technique that is used is called as the inverted. So in inverted dropout, what you do is you have then what you do is like you try to find out what should be a set of activations. So instead of physically removing a neuron, what you do is you have these neurons in place, but you try to find out which activations in this layer should be masked and which should not be masked. So with some probability, which is you keep Bob, what you do is you find out which neurons in this layer have to be kept and which need to be removed. So you try to create a mask. I create a mask, then multiply using this mask and something. So then I element wise I multiply this mask with the, so I will be able to have, I do a multiplication of the mask outputs, and then I will drop some of the, so the output from this neuron will be only 0, and subsequently all these weights. So all these outputs can be. So now what you also do with respect to this dropout, inverted dropout, is that you correspondingly scale the output from the, say for instance, if key prop was 0.8, you also, after performing this step, you try to multiply all the other activations by 1 divided by, multiply all the other neurons by this. So what you have is like you are able to perform something called as the in. So uh, when you use this deal, you use the same for both the forward and the back propagation. So it means that whatever layers states needs to be done, it's the same here. And but it can be different for different iterations. So different passes, different training examples, I can use. Say I am training my thing using a for loop from 1 to m. So for different training examples, I can use skills, or I can choose like how I want to use. And during after using doing all this, you update the weights, and some of the weights will be suboptimal, some of the weights will be optimal. So use this combination of optimal and suboptimal weights to predict the output during the test time. So it means at test time we don't use the, so now so as we already saw, like it has the effect of knocking out the elements in the network. So every time you knock out some of the neurons, like you are working very effectively. So so we can say that like dropouts also have a similar effect. So another important thing is that you can have different probabilities for different key proofs for different. So different. So it means that in each of the layer, so you may have several layers in a neural network. You may have here a dropout of 0.8, maybe 5, 0.9, and so on. Key proof. So it means that with respect to this layer, only out of 10, there is a chance of 2 getting. In this layer, out of 10, there is a chance of 5 getting. But here, out of 10, 1 getting. So you may have different probabilities for. So typically, what they do is, with respect to input layer, they keep the dropout equal to 1 because they don't want to eliminate lots of. So uh, now the downside is that like it gives more parameters. So now you have say 100 or maybe 20 layers. Now if you have different dropouts for every layer, so this becomes another hyperparameter. So dropouts become another hyperparameter that you use to search. What I do is like I have a single key prop, but I decide which are the layers which need to be affected by. That way, I have only one parameter. So typically, like dropouts are often vision because the images have large input size and overfitting, and there is not much of data. So with any, as I told you, medical imaging problems, not much of data is available. So overfitting is the usual. So fault is the. So uh, now one of the issues, like when you use this, is that because you keep varying the layer nodes, like which are dropped, the neurons which are dropped, the cost function cannot be very. So it means that like whenever you plot cost function at that time, so so it means that you turn off the dropout and the code and say easy. Now, another method which is useful with respect to regularization is called as the data augmentation. So with respect to data augmentation, so data augmentation helps. It means less data, you're going to have high overfitting, which we say as high variance data. going to have the problem. We have the problem of high variance. Now, in order to avoid this overfitting, then eventually avoid high variance and increase the data. So one way to increase the data is by using the data augmentation. So now you may data augmentation. You have an image, then you try to wiggle this image. You try to rotate this image. You try to flip this image, and you try maybe horizontal flipping, maybe vertical flipping, and so on. Maybe zoom this image, right? So and so on. Like, and you try to create more samples by finding more samples out of this input image. It means that eventually you are increasing the data size. So by virtue of increasing the data size, you are able to use the. So this is true with respect to OCR data set, optical character recognition data set. So here also you can create rotations, distortions. So with this, like, I'll stop here. So if you have any queries, I'll take. Any queries, you can just let me know.
Hello, sir. Now audible?
Yeah,
Yeah.
yeah.
Sir, I just want to know, you just explain the augmentation with related with the images. Okay, we can flap, swipe, or rotate the image. But if it is a numerical form of data available, then what can we do in that case? Because the problem which I faced over in my problem is a minority class is there, no? So I have very less number of samples in that scenario. So what should I do? Come up with a good amount of samples.
So your output variable is a numerical variable.
Yes. Data is also numerical. It's not a image format data. So I can't go for that flapping, swapping, or rotating. This kind of things are not applicable in that case. No. So other than smooth or smooth E, is there any other technique to go for creation or for that augmentation stuff?
So you can try very selectively. You can try introducing some noise in the data. So using any of the distribution, you can add some random noise into the data on some variables. At least you can try that.
Okay, sir. Thank you.
Hello, sir.
Yeah.
Hello. Am I audible? My
Yeah,
question:
yeah.
augmentation can be done in two ways. One is using the full image by rotating, shifting, or something else. Another way is that by cropping a part of that image. So which one is better? I am copying on full image for let 50, randomly cropping of a fixed size. That is one way I can increase the number of images, or another is by flipping right way or shifting the angle in this way. There are two methods, different methods. One is the number of pixel.
Yeah, so if I ask you a counter question, like say, what is the purpose of augmentation?
To increase the number of images as a to train the network.
So So basically, like as we saw in these examples, so the purpose of augmentation is not to make your model more accurate. It is basically to make it little underfit. I mean, it is to make your thing little suboptimal.
On
See,
problem with this,
yeah.
basically
So what I
image
mean
processing
to,
data.
yeah, image processing data. So see, the thing is like when you use very deep networks, they are highly highly capable of learning all the images. Now, with respect to images, like you don't have you have the problem of overfitting, because you have say 100 images, your model can easily learn all the patterns in the 100 images. Now,
But
your objective is,
my objective is, as I am working with the medical images, in the medical images, to train a deep network, we require more number of data training images. But practically, we cannot get more what is required for train that deep learning successfully, that we are not having. Just like I'm considering that fundus images having the drive data set, it is having only 40. But to train a network unit like unit, we require thousands of images. That time, how I can augment these many? This is my problem actually. This is my question.
yeah, I understood your question. So, see, if you ask me, like straight away, what should I do? Then I will say that there are many augmentation libraries that are available. So, in those augmentation libraries, you can just check on internet Python augmentation libraries. So, those augmentation libraries themselves directly provide you all the different types of augmentations that are possible in the images. So you can use those augmentation libraries and augment your images. That is the straightforward answer. But
Yes, sir.
Yeah. So but
It is okay.
but the,
It is okay that I am talking, but my question is that whether full image augmentation is better than the cropping image augmentation. That is my question actually.
see, it is always better to have a full image augmentation. See, why do you do augmentation? You're trying to give your model more varieties, right? So your varieties should be more similar to what may be the input.
Yes.
See, if you're never going to give only a small part of the eye as input, then why are you going to compress your image and have an augmentation like that? Right, within the scope of whatever may be the different type of input, there you try to create more variations. I mean, that will be always better. Say, for instance, you never have a horse which is upside down. So then it is not at all necessary to train your model with an image which is vertically flipped.
Okay. Thank you, sir.
Yeah. Yeah, recordings of these sessions will be shared. So many people have written not properly audible.
Hello.
Yeah.
Good afternoon, sir. Am I audible?
Yes, please.
Yes, sir. Actually, I just wanted to ask, sir, is there any change of the results or the interpretation if we divide the data set into just two parts and if we divide the data set into the three parts? Because sometimes we see that the algorithm is tested by dividing the data set into just training and testing, and sometimes we see it is divided into three different, like the way you explained. Sir, does it means does it have any difference? Or and I just want to ask one more thing, that sir, how to find out the optimal number of epochs for training the model?
So first question was about division of the total number of samples available. So there, see, mostly like these days people do with two data sets. If you have, and if you because like testing is not going to be, there is not going to be a feedback with testing, but there is always a direct feedback with respect to dev set, right, or a validation, because validation set is what you will be repeatedly using for updating your parameters and hyperparameters and so on. So it is quite useful to go with two data sets, two divisions. If anybody, if publicly there is a benchmark, if there is a benchmark that is available publicly, then you can go for that as the test data set. Right. So in the absence of a public benchmark, even if you have test data set, then your test data set results are going to be different from somebody else who is working on similar problem. Right? Because the samples that are there in your test data set will be different from those that are in his test data set, even if you have a similar proportion of divisions. Second question was regarding
Yes,
the optimal
epochs.
optimal
Yes, sir.
epochs. Yeah, so optimal epochs. So I think once more that depends on like how you're converging, how your solution is converging. If your solution is converging too early, then you may have to allow. You need not allow too much of a epoch, because like it is already converging and there is not going to be much difference, because we have already seen that there are possibilities of uh, your solution not going to become optimal, because maybe somewhere the activation functions have reached their saturation points. So it all, I mean, it depends on where your convergence point is, right? So maybe like after your convergence, you can allow for 10, 20 epochs and see like how it is. So you don't have a global number.
Yes, sir. Yes, sir. Thank you, sir.
Difference between the data set is divided into trainings times the average training set is equal. See, validation. Okay, so see in training set validation 10%, test set 20%. You leave the test set 20%. Okay, so you let us assume you have 100 samples, then you have say training set as 70% and 10% as the validation set. Then what you can probably do is like this 10% validation can come from this 80%. So you have a training set of 70%, you have a validation set of 10%. Now you assume this 80% as the 100, right? Now you can do a k-fold cross validation, right? So now you put this together, then you do a k-fold cross validation, and then you select your model. So once more here it says 70-10 means maybe you can have a k-fold validation in the sense that you can choose out of this 80, you can choose any 70, once more train, validate it on 10% validation. Once more choose another 70, or like you divide it into 10 parts and 8 parts, and then use that k-fold thing there. I mean, all possibilities are there. So what you do is you have this 80% data set, right, which is the training set of 70% and validation of 10%. Now, this training set of 70 is divided into say 10, 10, 10, 7 times. And then every time, like you try to use different 10% as the validation, and you keep training your data set and checking using the validation set. Dev, and the difference between dev and test is dev is for basically the validation part. So test is like, as I told you, if you have, it makes sense only if you have a public reference or a benchmark data set. You can just test it on that data set and say that like my model has this much amount of accuracy. So how weights are calculated? Weights are initialized and then they are updated. Is the training data set used for validation, or is there any as validation set data set? In most cases, they give us training and test data set, like that they give. So, or they do not give any, they just give only the data set, and it is up to you to train and test using whatever by making a division. So in some cases, they may give a test data set, training data set, validation set, and they may give a test data set also. So mostly in these competitions, they may give such kind of three things, wherein like they may not make the test data set public, but they will take your model, then they will check on their data, on the data test data set, and they will say you the results. Okay, so I think so we will disperse for now, and we will come back at 2:30.
Excuse me, sir. May I come in?
Yeah, yeah. Please.
Yes, sir. I have a very simple query, which is regarding activation function. Can we have a different activation function for each layer, like in a
Yes, you
single
can have.
Yeah.
You
And
can
how
have.
do we decide it?
Morning, I was saying about few things, right? Say, for instance, it depends on what kind of problem you have. See, with respect to the intermediate layers, people these days are not going for sigmoid or tanh activation function. The reason being, uh, if they get into those saturation points, then moving away them from those saturation points is very difficult. Saturation points means those extremes. So sigmoid has a range from 0 to 1. So when the value of Z is very high, then sigmoid gives an output of 1. If the value of Z is very low, then sigmoid gives an output of 0. Now, once sigmoid starts giving an output of 1, then you need big change on the input in order for you to bring it back to somewhere like where the weights can change. So are you able to follow this?
Yes, sir. Yes, sir.
Yeah. So now ReLU is most commonly used. Now what kind of problem you have? If you have a maybe multi-class classification problem, if you
Yes.
have you have a binary classification problem, if you have a regression problem, then it becomes your choice on how you should, what activation function that you should. So maybe for a binary, you may use a sigmoid in the output layer. Maybe you can use linear function in the output layer, ReLU once more in the output layer for regression problems if there are no negatives. So it depends on like what kind of problem you have at hand.
Okay, thank you, sir.
So I have one more announcement to make. Please don't log in with some numbers and some generic names. So because attendance will be a problem, you will be marked absent and then it will be difficult to revoke. So please, when you join, you please join with your registered names or email IDs. This is my request. Please, in the coming sessions also, please do not join from generic. We should be able to identify you, otherwise we will not be able to mark your attendance. Is that okay? So we will meet at 2:30. Thank you.
Thanks.